All right, hey guys, I want to talk about how to paddle into waves fairly easily and why you might be paddling really hard to get into certain waves and why you might be paddling with very little effort to get into other waves. So it all has to do with what's called planing speed and the speed of the wave. So matching first getting to planing, meaning you're up out of the water and you're skimming on top of the water. And the second part is making sure that you're catching up to the wave speed moving into the beach. So I've pulled a couple examples. I'm going to walk through some of these examples with you. One is Mason Ho actually paddling quite hard to get into this wave. So let's take a quick look at what that looks like. Boom, now he's in and he's going. I'll watch it again. And then we'll do it in slow-mo, maybe it had quarter speed, and see what that looks like. Now this is quite the mutant of a wave, but what this is going to show us is kind of the hard part. Why would we have to paddle hard into a wave? Now the number one thing that we need to do is we need to catch up to the wave's speed moving into the beach. That is the speed at which we need to get to in order to catch a wave. Now, the shallow water wave formula, and I've said this in other videos, is a formula that we can use to somewhat benchmark how fast a wave is moving into the beach, which therefore means how fast we need to go in order to catch that wave. So when we take a look at maybe the height, and it's based off the height, when we look at the height of this wave from trough to crest. Now this is not going to be Hawaiian size, but this is going to be true height size. I'm going to go ahead and estimate this at, say, a 10 to 12 foot wave. When we look at the wave speed formula for the shallow water wave formula, we're looking between 10 and 12 true height feet. And that wave is probably moving between 14 and 15, maybe 16 miles an hour. So between 14 and 15, let's say. Let's give them the benefit of the doubt that it's moving slower. So we're looking at something that's moving between 14 and 17 miles an hour, roughly, into the beach. And so Mason needs to catch up to 14 to 17 miles an hour in order to catch this wave. There's a couple things going on. One, when we paddle on a shortboard like this, we can't paddle, even at sprint speed, more than 3.5 miles an hour. And I've showed that in other videos. So when we're looking at catching this wave, we have to get up to at least 14 miles an hour, and we can only go 3.5 miles an hour paddling. There are other forces we need to tap into. One of which is the momentum of the wave moving into the beach, just like we were talking about. If this is moving in at 14 miles an hour, the waves are orbital as they come in, and they continue to be orbital as they start to break. So as this breaks, as it starts to lift, the top of this continues to move forward, and there's still forward momentum and forward force. And studies from Scripps Institute actually show that for a breaking wave. And this is still continuing this way. So we could actually still technically outline that this wave's energy is still orbital at this point before it breaks. Now, the momentum's only going to get us so far. The big whopper that really gets us into these waves is just the same force that we would use in order to drop into a half pipe on a skateboard, and that's good old gravity. So when the ramp is steeper, you get more gravity. So we've also calculated for shortboard versus longboard drag, roughly, how fast you can accelerate given the different degrees of the ramp. So a 10-degree ramp will get you to just below 2 miles an hour in a second. So it accelerates in about a second. But a wave actually changes. It might go from 10 to 30 to 65 to 90 all within 3 seconds, right? That's a very fast transitioning wave. Or it might be something that you might see at, say, Old Man's in San Clemente, where it goes from 10 to 20 to 30, maybe 45, and then it just starts spilling over. Right? And so and this happens within, say, a 5-second period. So the transition is very slow. So when we're looking at 14, if we were to not paddle at all and just wait for gravity, then Mason would have to wait until that wave was about 45 degrees before he even hits 14 miles an hour in 1 second. We also need to factor in the time to actually get to our feet. So the pop-up ranges between around 3/4 of a second, 3/4 of a second to about a second and a half for most of us. And the pros have been clocked to pop up, depending on when you start the pop-up motion, a little over a half second to about a second. Again, depending on how you measure that. When we look at this, he's fairly flat here. You can see that the ramp is not very steep, and he's also way in front of the top of this wave. There's actually two waves here that end up merging together, and this is another great example of how the top of a wave could have a lower ramp. You can see here this ramp is not very big, even with the poor camera angle. This isn't exact. It's actually going to be probably more like that if we were to turn the camera so that it's completely side on. But let's just use this for an example. When we look at that versus when we look at this, what a difference that is. The lower part of the wave versus the higher part. Now, if the higher part has a lower angle than the lower part, then that's usually a perfect formula for getting pitched, depending on where you are on the wave when you catch it. So if you're at the very top here, you're definitely going to get pitched. I don't usually say always, but in this case, I feel really confident that if you're up here, you're trying to catch this wave, this angle is not going to steepen up enough so that you can get the extra speed you need to get down the wave faster than the bottom part. The bottom part's already has exceeded the ramp on the top, and so therefore this is where most of the energy is, and this is where the speed is. This back wave is probably going to catch up to the front wave, and so if you're up here, you're going to get pitched. What Mason has realized is exactly that. He says, hey, you know what? I got to get out in front of this thing. And so he is trying to furiously, and you can see at the very beginning of this, he's already been paddling fairly hard. I'd say 2 or 3 strokes with a lot of kicking to get to this starting frame. But he's still very flat and very submerged in the water. When we talk about displacement vessels, on shortboards we are displacement vessels. Our body and our board are submerged in the water. Once we make it to planing speed, we can start to stand on our board without the board sinking in the water. The upward force is pushing back so that we don't sink. The problem here is that he needs to go faster than the minimum planing speed for this board. He needs to go 14 miles an hour in order to catch the wave, in addition to planing speed. So the first thing that actually happens for him is he has to get to at least planing speed. That's the minimum requirement. If he's at planing speed, then gravity will actually take him the rest of the way to catch up to the wave. Now, my big philosophy is that if you can get into a wave earlier at a lower angle, you have more time to then pop up to your feet by the time it steepens to the point where it's very difficult to navigate and negotiate that transition to the next section of the wave. He could just sit on the inside in here and wait for the wave to come and wait for 45 degrees. But then the fact that we need to time how fast it goes from 45 degrees to an angle that is absolutely impossible to navigate given the board that he has, to see if he even has time to get to his feet in that time period. So he's giving himself the best advantage that he possibly can by trying to get in front of this wave with his paddling. So what you'll notice here, watch the nose of the board. Here he's submerged in the water, he's in displacement. We're first watching to see when does he go into planing mode. He reaches planing mode right about there. Right about there. See how that nose pops right out there? So this left arm stroke right here, this left arm stroke right there, boom, helped him get through the whole speed barrier, the HULL speed barrier, the whole speed barrier, to get him up and planing. I've talked about it in other videos where the whole speed barrier, getting through that barrier, takes the most amount of energy for a vessel. Once you're planing, then there's a lot less drag. And so these extra strokes that he's doing here is one, to get him out in front of this lower wave. He needs to go further down so being up here, he needs to get down here in order to stay in front of that wave. It also is allowing him that extra burst speed to catch up to this speed. Remember, he's got to go at least 14, 15 miles an hour before he catches the wave. So right after this next left arm stroke, so first left arm stroke takes him to planing right there. He's planing. This is going to help him sustain that speed. Even though you're planing, you may not be sustaining or gaining on that speed at that point. If he took this one left arm stroke and stopped paddling, he's going to roll right out the back or top of the wave and move back into this area of the wave. And as we talked about earlier, it's not steep enough to take him down the wave. This will actually float him out the back of the wave or pitch him over. So he needs to take these extra strokes. And this next left is when he reaches right there, right here. This next left right there, straight back power gets him down and into that 14 to 15 mile an hour range. That extra stroke right there is just a little bit extra for rhythm's sake. And then when you take a look at when he starts his pop-up, which is right about there, look at kind of the angle that he's at. He's nice and steep. And then by the time he gets to his feet and set, you can see it hasn't changed all that much. So the rate of the change from there to there, actually let me match these kind of side by side. So the rate of this change of the angle hasn't changed all that much by the time he gets to his feet, right? Now, I want to compare this rate of change to this section of the wave. Why is he taking off way back here? Well, let's go back to when we start his pop-up right about there. You can see that this is a steeper angle, or a little bit steeper than before. And now by the time he gets to his feet right about there, you can see how much steeper that angle is, right? So when we look at the rate of change between where he starts his pop-up to where he ends it, this section of the wave, much faster rate of change than where he's at. This gives him extra time to set his feet and then negotiate the next section of the wave. So right here, this is a great example of Mason Ho getting into a wave where he has to paddle quite hard, but not because paddling hard gets him up to the speed of the wave, but paddling hard gave him the positioning, the timing that he needed in order to tap into gravity and the momentum of the wave to get down it. If we were to watch this, he only takes about, so if he's taken maybe 2 sprint strokes before this, there's 1, 2, 3, 4, there's about 4 strokes there that he takes. And that's it. So let's watch that again in slow-mo. There's 1, 2, 3, and that's not even a sprint stroke. So it's 3 sprint strokes plus maybe 1 or 2 prior to that just to get him going. But what you notice is that he goes from pretty flat water, submerged in the water, to planing on the water, and then tries to get out in front of that section in order to drop into this wave, get barreled out of his mind, and kick out.